Hey everyone, in today's lesson, we're going to talk about confidence intervals. So it's a bit of a larger lesson today. So let's get started. Just to get us thinking about this idea, I'm not sure if lakes are open or not right now, but fishing is popular in parks like Algonquin. I have a couple of lakes around where I live in Guelph. That normally are open this time of year. Um, um, but at Algonquin, many lakes in this park have brook trout as well as lake trout. I'm not sure. I don't think there's any trout around my area, um, but it's important to collect data on fish populations. Like biologists need to know like what percentage of fish are lake trout, what are brook trout, how much are pike, and they want to get an idea of the ecosystems and make sure they're healthy, right? Because if there's any big changes over the course of a few years, there might be something wrong with the health of the ecosystem. So the first question is, how can researchers determine reasonable estimates of the number and species distributions in a large lake? And why is it not possible to obtain exact numbers? So hopefully that's obvious to you. Like you can't just go out and catch every fish in a lake and count them all, right? So instead, like they might catch 1,000 and see how the different types of fish are distributed. If they catch 1,000 fish and like say 250 are lake trout, well then it may seem reasonable to assume, okay, that's about 25% of the fish are lake trout. But how confident could we be in that answer? So if we take 1,000 fish and find that 25% of them, that population is lake trout, how confident we could be in making a statement that the whole lake has 25% lake trout. This brings us to the idea of confidence intervals. So I've given you guys a document to kind of help you get ready. And I'm going to do these exercises along with you guys just to make sure I'm practiced up too. You'll need your standard normal distribution tables. And in part one, we're looking for some specific Z-scores. We're looking for the two Z-scores such that 90% of our data lies between those two Z-scores. And I'm sure many of you guys have kind of hopefully figured this out, that if 95% are between those two guys, then 10% is outside those two guys. So 5% on each tail. And this is symmetric, so we really only need to look up one of these. So we're looking for the Z-score that corresponds to a probability in our table of 0.0500. That's 5%, right? So can you guys look in your table? I'll look in my table too, and we will try to find this Z-score that corresponds to 5%. So I've got mine out here with me now. So it'd be on the negative side for sure. So we're looking for 0.050. And what you probably found is that there's kind of a tie. I'll show this over here. There's a tie. And the tie is between Z equals negative 1.64 and negative 1.65. So what we can do is we can actually split the difference. So, we could say, how about negative 1.645? Now, we don't need to repeat the same process for up here. This point would have 95% of the data lower than that. And we don't need to look that up. It's going to be symmetric. It'll be Z-score, a tie between positive 1.64 and 65. So, but we can just make use of that symmetry and say, 90% of the data is going to be between those two values. Let's repeat this for 95%. So 95% of the data is within, and again, these would be two different Z-scores. The number will be bigger than 1.645. So if 95% is within those two guys, then that leaves 5% outside or 2.5% in either tail. And so this time you guys are looking up 2.5%, which is 0.0250. And I'll do this too. 0.0250. All right, so I got pretty much -1 point. Hopefully you guys got this too, because I got an exact value. Where's my cursor? There it is. I got -1.96. -1, or then +1.96, excuse me. I don't need to look up the 99.7, or sorry, the 97.5. Because I know it's symmetric, it's going to be the same value. So 95% of the data lies within a z-score of -1.6 to +1.96. And we'll do this one more time for 99%. So that means 1% is outside the range, which means 0.5% is in either tail here. So can you guys look up the z-score for 0.0050 as best you can? I will do it too. 0.0050. And what you should find here as well, if you're using the table that I gave you guys, is that there's another tie between, and just double check, -2.57 and -2.58. So we'll say -2.575 and -2. Or in positive, I keep doing that, positive 2.575. We'll split the difference. So what we've been doing in these 3 exercises is we're making basic confidence intervals. We know that 90%, for any normal distribution, 90% of values will be between -1.65 and +1.65 z-scores, approximately. And 95% of data will be between a z-score of -1.96 and +1.96. And then for 99%, between about -2.58 and +2.58. And this is true for any normal distribution. So we can be, in this particular one on the screen here, 99% confident all of our values will lie between those 2 specific z-scores. We're not saying 100%. Like obviously there's a small chance in either end, but we can be really confident, more confident than we could with a 95% or a 90%. So we've got those z-scores now. Let's do something with them. So let's say that, and I've made this example up like a while ago. There's no Raptors game last night, although they're replaying a lot of the games. Fortunately, DeMar is no longer with us. I guess you're dating when I made this question, 2016 playoffs. So TV viewers tuned into an average of 1.75 hours of the Raptors game last night with a standard deviation of 0.5 hours. And we're going to complete this statement. So 90% of viewers watch between how many hours and how many hours? And you guys can do this because you've got, so we'll call our z-score formula, right? We rearrange that. We've done some of that to find a data value corresponding to a z-score. And you can do this for any normal distribution. If you have the mean and standard deviation and the z-score, you can actually turn those z-scores into meaningful data. So here we've got the mean and the standard deviation. And for 90%, you've got the z-score too. At 90%, the z-score we got was -1.645 and +1.645. So can you guys repeat this 2 times? Do it once for -1.645, and that will give you the lower bound, and do it for +1.645, and that will give you the upper bound. And then you'll be able to say, hey, 90% of viewers were probably between these 2 values. So you might want to pause the video and try that and unpause when you're ready, because I have the solution for these next few done already. So here we go. So if you take that negative z-score and plug it in, you get about 0.93. And if you plug that positive z-score in, You get about 2.57. So we could say, hey, 90% of viewers were reasonably sure watched between 0.93 and 2.57 hours. So we've taken that exercise we did earlier and just transferred it to some real world results, getting the actual hours watched instead of just some vague Z-score. So can you guys do the same thing for 99%? Remember, we have the Z-score for this one. The Z-score for this one you guys can use is negative 2.575 and positive 2.75. Do those both with the rearranged formula to get a range of values. Unpause when you're ready. Here's the solution. So using our negative and our positive, you get about 0.46 or just under half an hour and 3.04 hours. So maybe even watching like the post-game coverage or whatnot, because most games are like 2.5 hours. So again, taking those vague Z-scores we had and just making a real world example. So we could be, 99% sure viewers watch, or that we could say about 99% of viewers watch between this amount of hours. Okay, now this last one has a different percentage, 80%. We didn't do this one yet. So you've got your mean standard deviation. You're gonna have to look up the Z-score for this one with one final exercise like earlier. You wanna find the Z-scores so that 80% of viewers are within those two Z-scores. And if 80% are on the inside, 20% is on the outside, and 10% is in each tail. Can you guys look up the Z-score corresponding to or closest to 10% or 0.1? Find that Z-score. It'll have a positive counterpart. Find a lower and upper bound. Give it a try. You can unpause when you're ready to. But here it is. So I got negative 1.28 and positive 1.28. And as we did in the previous two, I converted those into meaningful hours watched. So 80% of viewers watched between 1.11 and 2.39 hours. So again, what we're doing is we're kind of making these confidence intervals where we can be 80%, 90%, 99% sure that values fall within a given range. In this last preparation question, I've given you guys X values. I've given you guys hours watched. So I've given you like a couple data values. And I've asked you for what percent confidence interval does this range represent? So what I've asked you here, so I've given you, so you guys you have the mean, you have the standard deviation, you can get the Z-score for this guy, okay? You can calculate that for the 0.875, and you can calculate the Z-score number 2 using 2.625. You have the X value, the mean, the standard deviation. And I've asked you guys to find what's the probability that a random person is between these two values. We've done this before. You'd find the probability associated with this guy, subtract the probability associated with this guy. That probability you get will be your kind of confidence interval. So we already saw, 80% was between 1.11 and 2.39. So this range is a bit bigger. So you might expect something a little bit larger, maybe 85%. I'm not sure. Can you guys do it? You can pause the video and try that. Unpause when you're ready if you want to check your answer, or if you just need some help and want to see what the solution is. Okay, so here we go. So I actually flip-flopped my order of subtraction first when I did this. So you should be doing 0.875 minus 1.75. So I found the two Z-scores. Where's my cursor? There it is. So I found my Z-scores. I went into my table. I looked up my probability, 0.0401. Looked up my probability, 0.9599. And we learned when we're doing probabilities that are between, I should just rewrite that a little bit. When you're doing like kind of between questions, oh, I think that was actually good. We just subtracted two probabilities. The probability that some random viewer watched between 0.875 hours and 2.625 hours was 0.9198. So it's actually a 92% confidence interval. So 92% of viewers watch between these amount of hours. So if you went through these preparation questions, and maybe you didn't get one right away, but after taking it up, you kind of understood what we were doing, you get the basic idea of a confidence interval. What we have to do today, we're going to introduce maybe a bit of new language, a new formula or two, and a bit of heavier math. But this is the basic idea. So if you understood that, you're in good shape. We're just going to do a few examples and kind of take it to the next level a little bit. So let's dive in. So we're going to learn about confidence intervals by kind of working through an example based on the motivation we talked about earlier. So I think this says Lake Lavier, but I don't speak French. So, but it's a big park, a big lake in Algonquin Park. In 2009, some researchers caught 911 fish, and 234 of them were lake trout. So they're trying to estimate what percent of the fish population is lake trout, because then they can do year after year, catch more fish and see if it's growing, if it's dying off. Like, these are important things to know, right? So what is this percent of lake trout caught in 2009? I'm going to call this little p, because we're going to use that in a formula later. So this percent p, we just find what percent this is. So it's 234 out of 911. 234 divided by 911. So we're going to use, so it's about 2.57 or 25.7%. So, I mean, it might be reasonable to say, oh, the fish population, this lake is about 25.7% lake trout. And this is a good quick estimate, but how confident can we be that this estimate is reasonable? I assume it'd be safe to assume if we caught more fish, would we get a better estimate? How confident would that one be? If we caught less fish, maybe this would be not as good of an estimate. So are we, 90% sure this is a good estimate? 95% sure? Like, we gotta actually firm this up a little bit. So how good of an estimate is this? This brings us to the idea of a confidence interval. Confidence interval is the range of possible values of the measured statistic. Here it's a percentage of a lake population that are trout at a particular confidence interval, a confidence level. So, for example, what we'd like to be able to say is, hey, based on this 25.7%, I want to be 95%. I want to make a statement saying, hey, I can be 95% confident the percentage of lake trout is between this and this. So maybe based on that, maybe 24% and like 27.3% or something like that. I want to be able to make a statement like that, saying I'm 95% sure the trout population is between this percentage and this percentage. That's our goal. That's a confidence interval. There's several steps we need to do in order to build that up. Finding this initial estimate is the first step in that. So it'll be a bit over 25.7%. It'll be a bit lower than 25%, this confidence interval. Let's keep moving forward. So the confidence level is the probability a particular statistic is within the range indicated by the margin of error. So we're going to get the margin of error in a second. But like in the previous example statement I made, this 95%, this is the confidence level. So we can talk about that now. That is the confidence level. But like you can, if you make your range bigger, you can say, well, if I'm 95% sure that my lake fish trout population is between these two percentages, well, then if I could be 90% sure that it is in the smaller range, because if you make a smaller range, you're not as sure you're going to be in there. Or I could be like, I'm 99% sure if I increase my margin of error a little bit, I can be 99% sure. So the bigger your margin of error is, the more confident you can be a range of values is going to be in there, right? So the common ones we use, usually 90%, so like 9 out of 10, 95%, 19 out of 20, and 99%, 99 out of 100. And these z-scores associated with these intervals, we've already done the legwork, so you know where these come from. So remember, we were 90% sure that data values for any normal distribution will be between negative 1.645 and positive 1.645. So that's where that came from. We got 1.96 for 95%. And if you recall, for 99%, we got 2.575 because we averaged. The more precise value is actually 2.576. So these are the z-scores we're going to use all the time for these different confidence levels. They'll always be given to you. You don't have to memorize those and re-look them up. We did that already. We know where they came from. We can just use them now. All right, so let's find what this 95% confidence interval is for the lake trout population. So to do this, we need the margin of error. So our estimate is 25.7%. Like, so is the margin of error going to be, is it going to be 2% above, 5% above? Like, we need to say, 25% plus or minus what margin of error. So the formula is this, and it is well beyond the scope of this course. We're not going to derive where this formula comes from. We just get to make use of it. Maybe in a higher level stats course in university, you might derive this formula. So to get the margin of error, you take the z-score associated with whatever confidence level you're talking about. So if you're doing in this case, for our 95% confidence level, we'll use the z value of 1.96. So this margin of error, you take the z-score associated with your confidence level times the root of, and I just got to make sure I get this. It's the one time a year I work with it. Yeah. You take p times 1 minus p, and you divide by the sample size. So n here is sample size. E is the symbol we'll use for margin of error. P is our population proportion. So for example, like in the question we're doing, the P is 25.7%. It's the proportion that is lake trout. And the z-score, that is just our z-score, which changes depending on our confidence level. And one note here, think about what happens as n gets really big. As n gets really big, you're dividing by a bigger and bigger number, and the margin of error goes down because you get a smaller and smaller number. So, and this is good, right? And this makes sense. The more you sample, the more likely it is you're getting an accurate result, and your margin of error will shrink. So just want to note that as n increases, the margin of error, E, decreases. All right, so let's find the margin of error for our problem. And we have all these things, right? It's just we got to use the formula. We got the sample size, it was 911. P we found, it was 25.7%, so 0.257 we'll use. And our z-score we've already got, it's 1.96. We just actually have to use the formula. So let's do it. Margin of error. Our z-score, because we're doing a 95% confidence interval. Just look it up. 95%, you're going to use z equals 1.96. Times root of. P was, and we'll use the decimal value here, 0.257. You do times that by 1 minus 0.257 and divide by the sample size. So maybe you want to do this in a couple steps. Maybe you're comfortable on your calculator. You can do it more quickly. It's totally up to you. But take a moment and do that. And I'm going to do it too. I debated doing everything by hand ahead of time because there's a lot of calculations today. But and then times 1.96. All right. So our P was to 3 decimal places, or 0.1 percentage points. So we'll do the same thing for our E. So I got, and you guys should double check this as well, 0.028. As a percentage, that's 2.8%. So guys, we got it. Our estimate of 25.7% is good within 2.8%. 2.8% above, 2.8% below. So the confidence interval is given by the following two numbers. So I'll just word it this way for now. So a lower bound and our upper bound. So our estimate was 25.7%. That's good within 2.8%. So subtract 2.8% from that and get a value, and then add 2.8 to that value. So just do that pretty quick. 25.7 minus 2.8, 22.9%. And 25.8, I'm ashamed that I'm not using mental math, but I have 2 kids and I'm tired. And 28.5%. So we can be 95% confident that the fish population, the lake trout population, makes up 22.9% to 28.5% of the fish's lake population. So the lake's fish population. So a researcher might summarize these results in the following way. And this is kind of the ultimate goal of making a confidence interval. You get your estimate. How good is your estimate? Well, we'll say the lake trout make up 25% of the fish population, and this calculation is considered correct within 2.8%, our margin of error, 19 times out of 20. So you might, sometimes you'll summarize the results without actually saying the interval, the range of values. You could just say here's my P, this is my margin of error, and this is my confidence level. And remember, 19 out of 20 is just like 95%. So it's a nice tidy way to summarize a confidence interval question. All right, so that was, it's a bit of heavy lifting, but it gives us a way to say, hey, how close is our estimate? And so let's try this one more time. Can you guys repeat this process to find the 99% confidence interval? So we've got our P. You got our N. Actually, instead of just writing a check mark, I'll actually write what it is just to help you guys get going, because I want you guys to try this one on your own. I've actually done this one ahead of time, but I'll help you get set up here. So what's changed? You got our P. P is still 0.257. Our N hasn't changed. N is still 911. What has changed is our confidence level, 99%. So when you guys are calculating your margin of error, which you need to make your confidence interval, you need to find that new Z score. So for 99%, this common one, we will use 2.576. So give it a try. Find the margin of error. What's the lower percent? What's the higher percent? If it's a bigger confidence interval, then the range of values should be, you'll have a bigger range of values. And then see if you can make a statement too. So try that, give it a try, unpause when you're ready. Or, if you kind of get stuck, you can just look at the answer, but here we go. So calculating our new margin of error with our new Z score, we get about 3.7%. So if we want to be 99% confident that this 25.7 is accurate, we have to now add 3.7 and subtract 3.7. So you get that we can be 99% confident the fish population, the lake trout population, is between 22% of the lake and 29.4% of the lake. Researcher might summarize these findings saying lake trout make up 25.7% of the fish population. This is considered correct within 3.7%. So again, these statements are kind of all the same. You get your P, you have your E, and if you'd like, you can write out the range of values, not necessary though. And this time, because we used our 99%, we say 99 times out of 100. All right, we've made 2 confidence intervals. We found 2 margins of error. Do one more, guys. So let's do another year, and we have a new sample being done. So we have 141 lake trout caught from a total catch of 689. So N is 689. P, it's a new P, right? 141 out of 689. I'm going to let you guys try that on your own. So just get P. This time we're making a 95% confidence interval, and so our Z value will be 1.96 again. And for these new values, you guys will calculate a new margin of error for this whatever P you get, and see what range values you get here. So I'm going to let you guys go for that. You can pause and unpause when you're ready. Here we go. So the new P, and I should say too, this is a fairly lengthy lesson. You're not going to have a ton of practice because we're kind of doing the practice together, right? Because this is kind of a heavy topic. So you're getting lots of practice as we do this. The new P is a bit lower, 20.5%. The margin of error is 0.030 or 3% when you use our Z score, our new P, and our new N. And you get a lower limit of 17.5%, an upper limit of 23.5%. So in this case, in this study, we can be 95% sure that lake trout population is between 17.5% and 23.5%. So let's talk about this because our previous P was 25.7% of the fish of the lake is lake trout. In this question, we got 20.5%. So like you might say, oh my goodness, the lake trout population is dying, right? It was 25.7% and now it's 20.5%. It's dying off. Well, we can use our confidence intervals to maybe shed some light on that. So if you look at our two intervals overlap, and they actually do, right? Our previous interval goes to its lowest value is 22%. And our new interval, its highest value is 23.5%. So yeah, our intervals do overlap. And I'll just say in brackets, they overlap in this range from 22% to 23.5%. So it's actually not reasonable to conclude that the percent of the lake trout population is going down because 23% is within both intervals. What could be possible, and is actually kind of 95% likely to be possible, is that the lake trout population was 23% of the lake back in 2009, and it's 23% again in 2012, and it never changed. So we can't conclude it's dropping. We can't say it's not dropping, like maybe it did, but we can't be sure. So we can't make any grand conclusions here, but at the same time, we don't have to. It's not all doom and gloom either, right? So yeah, this is just a little example of what's done with confidence intervals in real life. We've made a few. We've compared some intervals together. We've done a few calculations involving margin of error. So in your document, you've got one more. So consider this your kind of practice. If you want to pause the video, or if you got something to do, you can come back later on and try this one. But in this one, I'm not sure if you guys are old enough to, you guys might have been born after this, but Montreal had a baseball team before they moved they spent some time playing in Puerto Rico, but now they're the Washington Nationals. Every year there's always a survey, hey, is baseball coming back to Montreal? And they're always doing surveys to see what the interest is. So in Montreal, 1,589 people were surveyed, And 69% were in favor of baseball coming back. So this is your P, right? This one's been given to you. P is 0.69. Looks like my word processor made that funny. That should just be E. Can you determine the margin of error for this survey at a confidence level of 95%? So give that a try. You can pause and unpause when you are ready. I think I'm just going to do this one with you. There we go. So pause and do it, unpause, and I will just play catch up here too. So 95% means our Z-score is 1.96 times the root of P is 0.69. And I know that 1 minus 0.69 is 0.31. So I'll just do that ahead of time. Save me some work on my calculator. Divided by 1589. So let's do that. 0.69 times 0.31, 589. Take the square root and multiply by 1.96. So I got a margin of error here of, I'm going to take it to 3 decimal places, 0.023 or 2.3%. The margin of error, 2.3%. This statistic, 69% in favor of baseball coming back, is accurate within 2.3%. To make our confidence interval, we just take 69% and add and subtract this margin of error, which was 2.3%. And so that gives you the interval 66.7% to 71.3%. So that's the range of percentages. So what we could say is that 69% of people in Montreal want baseball to come back. The statement is accurate within 2.3%, 19 times out of 20. Or you could say we're 95% confident that 66.7% to 71.3% of people want baseball back in Montreal. One last type of question to do for you guys. Now, you guys have all the tools to do this kind of question on your own, but I thought I would just do it with you as well. So a second survey at a confidence level of 95%. So remember, that's giving us we've got our Z-score is 1.96. Found that 56% were in favor. A new P, 0.56. With a margin of error of 5.2%, our margin of error is 0.052. We can actually figure out how many people were surveyed. And to do this, we're going to rearrange our margin of error formula. So take that formula, Z times the root of P times 1 minus P over N. I'm going to do this rearranging with you guys. Our goal is to get N by itself. So to do this, N's buried inside a square root. So I'm going to square both sides. So on the left, I get the margin of error squared. Excuse me. On the right, I'm going to square Z squared. And when I square what's in the square root, I just get what's inside. So I'm going to have my P, I'll have my 1 minus P all over N. And I can get the N by itself by multiplying it up. N times E squared equals Z squared times P times 1 minus P. And then you guys have a formula that you can use. The number of people is the Z-score squared times our proportion times 1 minus our proportion divided by the margin of error squared. Let's try it for this one. So 1.96 squared times 0.56. 1 minus 0.56 is 0.44. And our margin of error, this question said it was 0.052 squared. Excuse me. Let's do this one together. You guys can do it too. See what we get. 10.44 divided by 0.052 squared. So you get pretty near 350 people surveyed. Nice. All right, guys, we did a lot today. What you guys should be able to do after today is, given a confidence level and a proportion, whether you calculate that yourself, be able to determine a margin of error and create a confidence interval. So for example, really the thing you should be able to do for sure is, here's this first one we did. You guys should be able to create a margin, find the margin of error. Find the lower and upper values, be able to state a range of percents that you're confident that the values between, and be able to make a statement like so. Use your proportion, your margin of error, and then whatever confidence level to make a statement like that. If you can do that after today, you are in really good shape. That's it for today. No other practice besides what we worked through here. In our next lesson, we're going to talk about random sampling and how confidence levels can tie into that. Yeah, I hope you found that okay. If you need to go back and kind of go over the lesson again to let it sink in, do that. But let me know if you need anything. Hope you guys are staying well, and we'll see you guys soon.